Welcome to week 8. I think there's two videos. Well, this one we're doing right this minute is going to be a video. Now, I was looking at week 8 and I clicked on it and it wasn't a video. So I'm turning it into a video. Now, there's another video in week 8 that talks about this and a little bit more about the 5 conditions for classifying soils in the Unified Soil Classification System. This is your coefficients. There's a coefficient of uniformity and there is a coefficient of curvature. Here's a big C and a little u, coefficient of uniformity, and here's a big C and a little c, coefficient of curvature. Now these are used in classifying fine grains, I think mostly in the Unified Soil Classification System. Now we went over the Casa Grande chart a little bit where that you had the U line, the A line, and all these lines, and it's called the plasticity or Casa Grande chart. And I made a little video of that and stuck it somewhere, I think in week 8. There's a lot going on right now. We kind of was in cruise control for a spell, but now all of this stuff is coming together at once. And I'm going to try to knock this uniform coefficient of uniformity and the coefficient of curvature out right now. Now, when it says curvature, look over here. This is a logarithmic, what would you call it, chart. So I'm getting to explain a couple of things at once. Don't worry about this blue stuff right now. None of this stuff right this minute. But let's just look at this graph paper right here. This is a logarithmic graph paper. Now look where it starts. It starts at 0.01. Now this is 0.02, 3, 4, 5, 6, 7, 8, 9, and 1.1. See, it was 0.01. Now we're 10 over here, so we're at 0.1. Now that's how we're going to read. This is a 3-phase chart, I think. Here's a phase, here's a phase, here's a phase. Now instead of using big numbers, we use little lines that get bigger and bigger, and they are accommodating logarithmic scale. And I'm not going to get into that. But that's how you read it. We started over here and we read to the left. Now, this is I call it the x-axis, and abscissa, they call it, and this to me is the y-axis. That's how they're talking to you. It has another name also, but I can't think of it right this second. But we don't need to know it. This is for the time being. This is x, this is y, and these read from right to left on the exit and from 0 up on the y. Now the part on the y-axis is measuring percent finer passing. Remember that. So now we get to use it. These are the size of the grains, the sand, the pebble itself. This right here, let's just say, and that's all in millimeters. Let's look again. We start at 0.1 millimeter and we go all the way over here, 10 of those spaces, and we're at 1 millimeter, right? Then we go 2, 3, 4, 5, 6, 7, 8, 9, and so forth. Now, I'm sorry, I left out some decimals, but you get the idea. I've already calculated them, and I've already determined their size. You get down to 1. This is 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that brings us up to 10 millimeters. Now notice some of these are 0.19 millimeters, and that is arrived at by interpolating. Here's 0.10, where, let me find it. This is 0.09. Let's see if we can try. This is 0.01, 02, 03, 04, 05, 06, 07, 08, 09, and then we go to 0.1. Got it? Okay. Now, that's reading the scale. Okay. This right here, this little curve is right away, if you're the engineer and you take a look at that curve, you're going to have good soil, well distributed, different size particles, well distributed. Now that's just why, because it looks like that. That look came from actual particle size calculation. You can't see over here on a regular log scale. We're going to be looking at over here. We're going to be looking at particle sizes versus where they are in here on these lines. Now we're looking at particle sizes as it relates to the coefficient of uniformity and coefficient of curvature. Okay, now it's defined. I've got my book in my lap, and when I get through talking, if I haven't totally confused you, I want you to go to page 9, actually 8 and 9. On page 8, it's where we will wrap up that problem. Remember, it was called example 2.1, and we had a sample of sieve and the size opening in millimeters and the mass retained up at the top left on that page 8. And as you went down, you begin to see the problem unfold. So the problem is example 2.1, and we're given an air dry soil sample weighing 2,000 grams. So that's our total weight. And mechanical grain size analysis, the lab data are as followed. So we got the mass retained. Let's go down here to this table 2.3, because it's going to cover the whole thing we're going to talk about when we're doing the cumulative percentage. Look at this chart while we're here down at when you get a chance on page 8 at the bottom. This whole thing's going to walk you through. And it starts with number 1. The percentage retained on each sieve is attained by dividing the mass retained on each sieve by the total sample mass. Okay, look down at the table on that page 8, and you will see, well, the percentage retained and the mass retained is 0, so the percentage retained is going to be 0. But I'm not going to go through this. We've had one video on it, and it's a well-written description of how to do cumulative percentage on that page 8. But while you're in this neck of the woods, I want you to go look at page 9, because page 9 is going to show you a SimLog graph paper like we're going to use, starting at 0.001 on the right of the x-axis, moving to the left, and then it's going to start at 0 on the x-axis and go 10%, 20%. Pay no attention to these numbers out to the left. They're dealing with something else that I well, you won't have it in your book, so never mind. But on the x-axis, you'll see it starts at 0, goes to 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That's the percent passing. Across the top, you will see the size of the pebbles, like 3/4 inch, 3/8 inch, the number 4 sieve, ever how many millimeters that is. If you want to know how many, you go over here on your back to your page 8 to your left there, and there is a chart giving you the 3/4 inch, and then the opening in millimeters is 19. It gives you 3/8 inch, and the opening in millimeters is 9.5. The number 4 sieve, 4 points. It gives you all that, and then it finally gives you the mass retained. So when you hopefully you understand how to calculate this percent passing. Now let's jump back over here, and I'm going to read just a little bit because I got this book, and I want the book to describe to you about this coefficient of uniformity and coefficient of curvature. In the book it says, upon completion, I'm on page 9 of these calculations. Over there on page 8, the grain size distribution curve is attained, and that's the curve up there in figure 2-2. So the by plotting column 2 over here on page 8, it's listed column 1, 2. By column 2, sieve opening in millimeters versus column 6, that's the percentage retained passing through on the SimLog paper. The percentage passing is always plotted as the ordinate. That's what it's called, the abscissa and the ordinate. And on the arithmetic scale, and the sieve opening as the abscissa. That's across the bottom. That's what I call x-axis. Now, what we're after, we're doing this because you need this information that we have are leading up to calculate in the unified soil classification system. If you read on down here, it talks about useful parameters can be determined from these grain size distribution curves. And it goes on to say that the diameter of soil particles at which 50% passes, 50% of the soil by weight is finer than the size, is known as median size, and it's denoted by D50. The D is the size of the particle, the diameter of the particle, and the little subscript 50 is the percent passing. And then the diameter at which 10% passes is called the effective size, and it's denoted again by the diameter D with a subscript of 10%, I believe, down there at the bottom. Yes, by 10. All right. Now then, two coefficients used only in the United Soil Classification System for classifying coarse grained soils, and that's seen in section 2.4, are the coefficient of uniformity, CU, and the coefficient of curvature, which is big C, little c. Now look down below, and it's defined as follows. The coefficient of uniformity is the D60, the diameter of the particle where 60% is passing. Now, we'll look on the video. Let's see where that came from. Here's 60% passing. I'm wiggling right there on it. And I'm going to draw a straight line over to the particle distribution curve, and then when it touches that curve, I'm going to drop straight down to the particle size. Now, what does that say right there? Let's count up and see. Now, I got, let me find, I've got D60 at 0.41 millimeter. Now, if I go over here to 0.1, which is right here, I'm going to say 0.2, 0.3, 0.4. I think I missed one. I've got over here 0.4, 0.41, just past this right here. Let me count it again. Where am I? Going from right. Take 60, go across straight down. I'm right here. So that is starting over again. 1, 2, 3, 4. That's 10. So I'm starting over here. 1, 2, 3, 4, 1. So 0.41 is what I've determined that particle size to be. Now then, and so forth and so on. I got it at 10% passing, going over and down, and I've got that at particle size at D10 to be 0.09, as you see right up here. I got it at 0.09 by counting over on my little marks. And then I have D30 at 0.19 millimeter. I have calculated or measured D60 is 0.41 millimeter particle. So now to find the coefficient of uniformity, I will take the D60 particle, 60% passing, and the diameter of that particle, and divide it by 10% passing and the size of that particle. That turns out to be 0.41 divided by 0.09. You can check me on this. That equals the coefficient of uniformity is 4.56. Now I've done the same thing down here. Here is D squared, the diameter squared in 30% passing, and I have that particle size at 0.19 right here. Now I've got to square that, and then I've got to multiply D60 times D10. It's hard to read. I'm reading two different things. And those actual numbers come out to be 0.41, as we found D10 to be, times 0.09. Now you have 0.98. That is the coefficient of which one? Curvature. Okay. Uniformity is meaning all the same. Now let me read a little bit more, because this is why we did it. So two coefficients used in this is classifying coarse-grained soils, see section 4, are the coefficient of uniformity, which are defined as D60 divided by D10, that's coefficient of uniformity, and coefficient of curvature is D30 squared divided by D60 times D10. Now we've done all of that up here. So realizing that we have arrived at these results for where's it, uniformity. We have 4.56. For curvature, we have 0.98. Remember, group indexes, don't get them confused, but just notice the size of the number or the amount that it says. Now let me say effective size gives the let me skip over that. The coefficient of curvature, coefficient of uniformity, and coefficient of curvature have little or no meaning when more than 5% of the soil is finer than a number 200 sieve opening. So keep that in mind. Figure shows some typical grain size. Let's see. Well-graded soils have particle sizes varying over a wide range and have higher coefficient of uniformity values. In other words, 15 or higher. Coefficient of uniformity values. Coefficient of uniformity is, let me find it again, 15 or higher. That means poorly graded soils have either, let's say, a deficiency or excess of some particle size. Most soil particles approximately the same size. In other words, uniformly graded soils, as shown in Figure 2.3. That's on another page. Are poorly graded soils because most particles are about the same size. You don't want that. And here we go. Uniformly graded soils have low coefficient of low coefficients of uniformity values, and they're called gap graded. And look at this coefficient here of curvature, and this would be a well-graded soil. I can't find it, but it has a low coefficient of curvature value, so it's a well-graded soil, and it's represented that way down and out. So that's a little bit more about this, trying to couple of things. If you go on to the next page, gosh, you'll see some different like particle size distribution curves, and the one probably that goes way from one side to another is gap graded. Well graded is the one that starts and just slowly curves and goes to the right. That soils all the way from 3/4 inches all the way over to way small, 0.01. So they're different size, and when your arc is covering those, and that's Figure 2.3. Gosh, I hope this helps you out a little bit. Don't hesitate to call me in this thing, but I'm going to shut it down from now. And if you're having trouble with this or any portion of this area of soils that we're in now, which is a little bit complicated, and it's really hard to comprehend when we all aren't in the same room, and we could discuss this. But I'm shutting it down from there, and I'm going to stick it in week 8 somewhere.